Now, depending on the exponent that is in our rate law, we can classify reactions into different orders. So a first order reaction is one where our rate is equal to our rate constant times, I'm just going to use A as our reactant in this case, raised to the first power. So this is what's known as a first order reaction. Zero order would be it's raised to the zero power, meaning it doesn't depend on it. Second order we'll talk about as well, where it's raised to the second power. Generally, you don't have higher than that for reasons of it's hard. We'll get into this when we talk about mechanisms, but it's hard to get three things that collide at the same time, which is usually what you would need to have a third order reaction. So generally, first and second order are the most common reactions that you'll see. So let's imagine a reaction where we only have a reactant of A going to B plus C, and we don't have any stoichiometric coefficients to worry about. And let's say we do an experiment, measure the rate law, and we find that it follows this type of formula here that I have. Basically, I've just rewritten this formula right here. So what we can look at is, what does this mean? What does this tell us about how things depend on time, and what are sort of the properties of first order reactions? Now we can substitute here, remember what rate actually means. It's a change in A as a function of time. And again, we're saying there is no stoichiometric coefficient to worry about here. And that is equal to some constant times the concentration of A. Now what we have here is a differential equation, right? Because it's an equation that involves a derivative as well as the variable itself. And this type of differential equation here is one that's very well known and fairly straightforward to solve. What we can do is sort of separate out the concentration dependence and the time dependence on two different sides of the equation. And we do need some initial condition to understand what's going on. So we say that the concentration of A, and this is generally something you need to do with differential equations, is provide some sort of initial conditions. We have to okay, the concentration of A starts at some initial concentration that we call concentration of A naught when the time is equal to 0. So we have to pick some time that's equal to 0 to sort of start our reaction at. Okay, and then we can rearrange this equation and put the concentration all on one side, so dA over A, and the time on the other side. So we're sort of treating this derivative as if we can separate it, sort of playing a little bit fast and loose with the mathematics here slightly. But this does work with the types of systems we're looking at, right? And this has a negative sign here. Okay, so then we can integrate from our initial concentration up to some arbitrary concentration, A, and we can integrate the left-hand side from our initial time t equals 0 up to some arbitrary time t. And this will allow us to solve the differential equation. Okay, so the integral on the left, we're going to 1 over x. We've integrated this a bunch of times in this class. So that'll give us the natural log of A over A naught, concentration of A over concentration of A naught. So that's a derivative we've seen integral we've seen a few times. And the integral on the right is pretty straightforward, just an integral of a constant. So we will get minus k times t minus t equals 0, which is 0. So we can say that natural log of A over naught equals minus kt. We can rearrange this. The more common way this is expressed is to take the exponential of both sides. So we'll get an e to the minus kt over here. And the new whiteboard is really like eating my inputs. And on the left-hand side, we'll have concentration of A over A naught, because we're taking the opposite of an exponential. And then we can say the concentration of A is equal to the initial concentration times e to the minus kt. So a first-order reaction has an exponential dependence in terms of what the of how the concentration of A changes over time. So the concentration of A will decrease exponentially from its initial value, and k is the constant that tells us how quickly that happens. So if we were to plot a function of concentration over time, so A versus T. There would be some initial value of A naught here, and then we would see an exponential decay. That's supposed to be exponential, even if it's not, where this is described by e to the minus kt multiplied by A naught. Okay, so in the next video we'll talk a little bit more about first order reactions and some other properties involved with them.